Hello everybody and welcome to our video on volumes. So what we're going to be talking about in this video is 3D solids for which we would like to find the volume. So I've got some three-dimensional figures here that we can take a look at. So this one, hopefully it'll work with me on the rotation here. This is an ellipsoid. So it's kind of like an ellipse extended into 3 dimensions. And what we've drawn here is a figure that kind of terminates at some, let's say, A and B. And what I mean by terminates is just that it ends at a specific X value, right? So it's got a fixed end here and here, and it's got this ellipsoid shape in between. Now, when we intersect this figure with a vertical plane, well, I'm getting ahead of myself. Let's consider how we find volume for a rectangular prism first. Just a real simple case. So if I've got a rectangular prism, it's got a base like this, and it extends upwards. Okay, so this rectangular prism will have an area for its base, and then it's got a height, and the way we define volume is the area of the base times the height. Okay, so how do we deal with that in a shape that isn't rectangular, right? That can't be divided up into cubes to measure its volume? Well, that's the tricky part here. So what we're going to do is we're first going to intersect this figure with vertical planes to get what's called cross sections. So imagine that I'm just taking vertical slices of this ellipsoid, and this is what you get. You get these shapes like this that look like flat cuts through the 3D space. So we call those cross sections. And consider the function a of x that describes the area of the cross-section that corresponds to each x value. So we've got a few x values here that correspond to where I drew these cross-sections in relation to the ellipsoid. And the idea is that each of these figures has an area. And so what I'm going to do is estimate the volume of the three-dimensional figure by partitioning the interval from A to B and taking samples of the area. So these are my area samples, and what I do is turn them into slabs that estimate the portions of volume. And that's what we've got in this third figure here. So notice what's key about each of these slabs is that the area of the cross sections of the slabs is constant. So you get just one area for each slab times the height, let's call it, of the slab, right? If we turn this to face this way, we think of each slab as having height, and then the cross section as describing the area of the base, in which case the volume for each slab would just be the area times the so-called height. So this then is our volume per slab. Right. It's the area of the base of the slab times the height of the slab. But because this thing is horizontal, the height of the slab is really our delta xi, the width of this interval on the x-axis. So if we add up a bunch of those volumes of slabs, that should give us an approximation for the volume of the whole thing. And then, as is natural, as we've done with other definitions involving integration, we say, hey, if I want the actual volume, I take the limit as the number of the approximating terms, in this case, these slab volumes. I want to take the number of those slabs going to infinity, and so that limit as n goes to infinity of the sum from I equals 1 to n of a of x sub I, delta x sub I, is by definition the volume. And of course, we know that the definition of the Riemann integral means we can write this as the integral from a to b of a of x dx. So to state this definition completely, let S be a solid that lies between x equals a and x equals b. If the cross-sectional area of S in the plane is a of x, where a of x is an integrable function, then the volume of S is the integral from a to b of a of x dx. That's what this says. So of course what that means is finding the volume of these three-dimensional surfaces boils down to finding an area function for the cross sections. That's the real challenge here. Now, for most of what we're going to deal with in this section, we're going to deal with what are called solids of rotation, solids formed from rotations. So let's take a look at that. And for that, we'll be able to use what's called the disk method. So imagine you have a curve, y equals f of x. So that's the black graph here, y equals f of x. And this curve, you take it and you rotate it around the x-axis. So imagine spinning this thing around the x-axis. And then you have to imagine taking a vertical slice of this. And because I'm spinning this thing around the x-axis, the vertical slice you're going to get is always going to be a circle. Right? You imagine taking this length of this line that goes up from the x-axis up to this point on the curve, and you rotate it all the way around. That's going to form a circle. And so we call that a disk. And it's a circle with some thickness. Now the radius of that disk is r equals f of x, the height of the function at that point. And so since all of our cross sections will form circles, what that tells us is that our area function will be pi times r squared. And in this case, r is f of x. So pi times f of x squared. And again, the width of this disk is dx. So I've got a graph here pulled up. So we're going to take a look at a picture of this to try to get a better idea. But that picture, we're going to relate directly to example 1 so that we can make this as clear as possible. So I'm going to start out by drawing this picture by hand. Then we'll show you an actual proper graph of it on screen so that you can see precisely what we're trying to get at. I usually will just draw these by hand, but it's a little hard to get the full picture with a rough sketch. So find the volume of the solid obtained by rotating the region under the curve y equals the square root of x from 0 to 9 about the x-axis. So the first thing you always want to do when trying to find these volumes is draw the original region. All right, and it's the y equals the square root of x. We know that that passes through 0, 0. All right, so from x equals 0, when x equals 9, I'm going to get the square root of 9, which is, of course, 3. And the square root graph is shaped about like that. And so the idea here is that you are taking this graph and you are rotating it around the x-axis. I could have done a better job on that second one. Let's try that again. Okay. So we've rotated this around. We've generated this three-dimensional solid. And the radius of each of these disks is going to just be the height of the function. Okay? So let's take a look at a better graph of this. All right, so here we've got our square root function plotted. And what I'm going to do first is turn on the rectangle approximations, right? So you've got each of your rectangle approximations for the area of the curve. Now imagine taking each of these rectangles and rotating them around the x-axis, right? So the green here is the y-axis, red is the x-axis. And so we're going to take each of those rectangles and rotate them. So that's going to be what we get when I turn on these settings here. And this program tends to be a little slow to adjust. So I got to pretty much turn these off to rotate it and change the angle. So let's try that angle, see if that's a little better. All right, so we see we've got a whole bunch of disks stacked next to each other. Each of these disks is approximating the volume for a portion of the rotation of the graph, and each of them has a radius that's the height of the graph at a point in the little subinterval. Okay, so let's move this out of the way and get back to the problem. So really, this disk should look more like a three-dimensional disk, like this. But when you draw these, the main concern is getting enough information out of the picture to set up your integral. So as long as you draw your curve, you draw your rotation, and you can label your radius and what your width for your disk is, in this case delta x, that's good enough for your drawing to make your work clear. Okay, so now we can go ahead and tackle finding the volume. And the volume is the integral from a to b of pi r squared dx in this case. And so our radius is just the function value. So this is from 0 to 9 of pi times the square root of x squared dx. Well, and that works out pretty nicely because the square root of x squared is just x. And this gives us pi x squared over 2, evaluated from 0 to 9. That's pi over 2 times 81. That's 9 squared minus 0. And so altogether we get 81 pi over 2. And that's it. That's really the whole idea, at least when it comes to solids that are rotated around a line. Now, we're going to do a few more of these for this disk method, because that's going to be really the most common thing you see in this section is the disk method, but we will deal with a non-disk case towards the end. Okay, so example 3, find the volume of the solid obtained by rotating the region bounded by the curves x equals 2 times the square root of y, x equals 0, and y equals 9 about the y-axis. So of course here we have multiple curves, so we're going to have to find intersection points for our curves, which shouldn't be too much trouble, because the curves are pretty simple. These are just a vertical and horizontal line, x equals 0 and y equals 9. So what's our function look like? X equals 2 times the square root of y. Now, most students are much more used to graphing functions that are written in terms of x, so you can do that here, of course. But what you have to keep in mind is, in order to write this as a function of x, I have to square both sides. But in this current form, there's a restriction that x is greater than or equal to 0 here, because the square root can only output a positive number, or 0. So when I square both sides, I get x squared equals 2y, but I still have that restriction that x is greater than or equal to 0, and so y equals x squared over 2. So changing its form to a function of x is going to be helpful, I think, for graphing this for most students, but it won't necessarily be helpful for integrating, for finding the volume. All right, so this is a parabola that's going to pass through 0, 0. Its vertex is going to be 0, 0. And we also need, where does it intersect with x equals 0? Well, you plug in x equals 0, you get y equals 0. So taking care of that. And you also need where it intersects with y equals 9. And that's pretty easy, right? So I plug in y equals 9. I'll plug that into the original function, y equals 9. I get 3 times 2 is 6. So 1, 2, 3, 4, 5, 6. Okay, so that's my function. And now we're rotating about the x-axis. So I'm taking a point on, or the y-axis. Y-axis. So I'm rotating about the y-axis. So imagine, let's draw a mirror image of our graph here. And you're rotating around that graph and it's forming a circle in 3D space. But the trick here is, what is the radius? So the radius is the length from this center of rotation out to the curve, and that's a distance on the x-axis. So we need the x value, but x is 2 times the square root of y here. So my radius is x, but written as 2 times the square root of y. And we need to write it as a function of y because the thickness of my disk here is being measured by the y-axis. So that's dy for integration. Okay, so with that in mind, we can now set up our volume and say, hey, our y values go from 0 to 9. So that's my bounds for my integral. And I get pi times my radius squared, and integrate with respect to y. Okay, I square 2 times the square root of y, I get 4 times y dy. And so this becomes 4 pi times y squared over 2, evaluated from 0 to 9, which is 2 pi, 4 over 2 is 2, times y squared, evaluated from 0 to 9. And so that's 2 pi times 81 minus 0. That gives me 162 pi. Okay, so we've dealt with rotating about the x-axis and rotating about the y-axis. So now what? So well, first of all, what do we see? We see that when we're dealing with these disks, if I rotate about the x-axis, the thickness of my disk is dx. So these rotations around the x-axis give me dx, so I need to integrate with respect to x. And when I'm rotating about the y-axis, I get these dy thicknesses for the disk, so I have to integrate with respect to y. Okay, so moving on, let's use this newfound skill to show that the volume of a sphere is v equals 4/3 pi r cubed. Well, in order to do this, using these skills, we have to figure out a way to represent the sphere as a rotation formed by some two-dimensional function. And I think it's easy enough to guess which function we should use: a circle. So if we have a circle with radius r, in fact, not a whole circle, rather a semicircle. If I have a semicircle, half of a circle with radius r, and I rotate that around the x-axis, then when I rotate that, I'm going to form a sphere. The trick is to figure out what the radius of each disk is, because notice the radius of this disk, which we'll write as rad, the radius of the disk is not the radius of the circle. It's actually shorter in this case, for this particular disk that I took, and it's a function of x. So we've got to figure out how to write this function. So what do I know? I know that for a circle, I get x squared plus y squared is r squared. So y squared equals r squared minus x squared. And y equals plus or minus the square root of r squared minus x squared. And I solved this for y because I wanted my function in terms of x, because that was the thickness for that disk that I drew. Okay, so I've got my picture, I've got my disk drawn. I have two functions though, and I have to figure out which one to use. Well, the positive version is the one to use because the positive square root is the top half of the circle, whereas the negative square root is the bottom half of the circle. So in other words, our radius is the positive root r squared minus x squared. Okay, now we can dig in and evaluate this integral. Volume is the integral, in this case from negative r to r, of pi times the radius squared. which is the integral from negative r to r of pi times r squared minus x squared. Now, this function here is an even function, and so we learned in Calc 1 that when we integrate an even function from negative a to a, we can just double that integral. And that should make sense because you can see if I take the integral from 0 to r and evaluate that, I'm going to get half of the sphere, so I would need twice that. Okay, so in other words, I can write this as 2 times the integral from 0 to r of pi times r squared minus x squared. And that's just going to make the integral easier to do. And last thing before I compute it, I'll just pull the 2 pi out in front. And so this gives me 2 pi times r squared x minus x cubed over 3, evaluated from 0 to r. That's 2 pi times r cubed minus r cubed over 3 minus 0. R cubed, 1 r cubed minus a third of r cubed is 2/3 of r cubed. This is 2 pi times 2/3 of r cubed. And 2 times 2 is 4, so that's 4 pi thirds r cubed. Okay, so we've just seen how to get the volume of a sphere, and it turns out we can use this type of approach to finding the volumes of many figures. Okay, but for now, let's just move on to something related, but slightly different, called the washer method. All right, so now we're going to be talking about the volume of a solid generated by a region between two curves, y equals f of x and y equals g of x, where f is greater than g is greater than 0. And to do this, we simply subtract the volumes generated by each curve individually. So what do I mean? If we look here, we've got this region between f and g, and let's say there's an a value and a b value here. So if we take that region and rotate it in 3 dimensions, it looks something like this picture I've drawn on the right. It's not a perfect picture, but hopefully you can get the idea, kind of like a clay pot almost. So it looks something like this picture. It's like this clay pot with an empty inside. And if I ask you for the volume of just the portion of actual clay, how do I find that? Well, I could take the volume of the outer figure and remove the volume of the empty space in between. And that's exactly what we get here. You take the volume of your outer figure minus your volume of your inner figure. And you can also simplify that by combining it into one integral, writing pi f squared minus g squared dx. The key thing is to think of this f of x here as your inner, or sorry, I should say that's your outer radius, the larger radius, and to think of g of x as your inner radius for your disk, for your washer, I should say. And I often get questions about why these are called washers. They're named for literally the little washers that go over a bolt when you're securing something, right? So those little spacers, metal spacers, that's what you should be picturing here, is that little spacer like that. Okay, so let's move on and do an example. Find the volume of the solid formed by rotating the region bounded by y equals x and y equals the square root of x about the x-axis. Now, as is usually the case, if I just have two curves, the first thing I want to find is intersection points between them. So I set y equals x and y equals the square root of x to be equal, so x equals the square root of x. And if I square both sides, I get x squared equals x. So x squared minus x equals 0. Factor. And solve. So I get x equals 0 and x equals 1. And so let's plot those points. In both graphs, when I plug in 0, I get 0, so y equals 0. And when I plug in x equals 1, I get y equals 1. So these are my two intersection points, and they look like this. So one of these graphs, we'll say in green, is y equals x. That's the straight line with slope 1. And the one in blue will be our square root of x, which looks like this. Now I'm rotating this around the x-axis, so I'll start with picking an x value. I take a point on that curve. I draw the mirror image on that. I'll do it the smaller curve first, and I rotate it around. Not like that. Let's try that again. I rotate it around and I get an inner disk. And so I'll just draw a little arrow here and call this the inner radius. And the inner radius is the y value, which is just equal to x in this case. And then I'll draw a mirror image of my outer function here, my bigger function. And again, we're calling it the bigger function because the distance from the x-axis, the y value, is larger. So I take this point and I rotate it around. And so this radius is what we call the outer radius. And that's the function y equals the square root of x. So when I go to compute my volume, I take my outer volume, pi, the integral of pi times the outer radius, the square root of x squared dx. And I'm integrating with respect to x because the thickness of my washer is measured on the x-axis. And I integrate from 0 to 1. And then I subtract the inner volume, pi times x squared dx. So again, this is my outer radius squared, and this is my inner radius squared. And just for ease, I'm going to combine these into one integral, the integral from 0 to 1 of pi, pi times the integral from 0 to 1 of the square root of x squared, which is x minus x squared dx. And now I integrate. X squared over 2 minus x cubed over 3, evaluated from 0 to 1. That's pi times 1/2 minus 1/3 minus 0. Okay, 1/2 is 3/6 minus 1/3 is 2/6. 3/6 minus 2/6 is 1/6. So this is just pi over 6. Okay, well that's it for that one. Let's tackle another one. So this time, this one's going to be trickier because now we're rotating about something that isn't just the x or y axis. So that really makes things a little more complicated, but not much as long as you're thinking about the problems in the right way. So find the volume of the solid formed by rotating the region bounded by y equals x and y equals the square root of x about x equals 2. So here's the trick. First of all, our region looks exactly the same, so I'm not going to recompute the intersection points and all that here, because it's the same graph. But this time, I'm rotating about this y equals 2 line. Or sorry, x equals 2 line. Should be careful. X equals 2. So that's this line. So if I'm rotating about this line, then what I want to do is go out a symmetric distance across and try to draw the mirror image of this graph over that axis. So it should look roughly like this. All right, so imagine you're rotating this figure. You see this mirror image here, but you're getting a whole 3D shape. I'm just not requiring that you draw the whole 3D shape. Now, since I'm rotating about this vertical line, that means my circle has to start at some y value here and rotate this way. And then I'll plot that same y value on the other curve and rotate this way. And so now we have to figure out the inner radius and the outer radius. Now, this is a little different. The inner radius is the distance from x equals 2 to this green line. It's the shorter distance. Remember, talking about a radius here, we're talking about a distance. So make sure you're always thinking about shorter versus longer rather than position, because even though the green function is further to the right, that doesn't mean it's the inner radius. We're looking at the actual length from here to the center of rotation. Okay, so if I look at that inner radius there, how do I get that inner radius? Well, it's two x values subtracted, x2 minus x1, right? I'm taking this point minus this point, but the curve has a lot of different x values. This one is fixed. The point of rotation is fixed. So this inner radius is 2 minus whatever x value I have here. But that disk has thickness delta y, dy. So I need to integrate with respect to y. So I have to write this as a function of y. X equals a function of y. Okay, so let's look back up here. We had this y equals x line. That's our green line. We need to write it as a function of y. Well, that's easy enough. It already is. X equals y. So we can just write this as 2 minus y. Okay, now we need the outer radius, and that's the distance from here, that outer chunk of the curve, to the same point of rotation. And so my outer radius is 2 minus the x value here. But again, we need to write this as a function of y, g of y. And so I look at my blue graph. That was y equals the square root of x. I need to write that as x equals. I just square both sides. I get x equals y squared. So we write the outer radius as 2 minus y squared. And that's the real challenge. If you can figure out the inner radius and outer radius correctly, then plugging into our general formula, pi r squared, is pretty easy. You just got to actually identify these things properly. So the first key step is always really carefully drawing your region and thinking about how to set it up. Now, one of the other things that comes up a lot is students will make little mistakes on the bounds for your integral. Remember, first of all, you decide which interval to look at based on if you're integrating with respect to x or y. So we've got dy here, and you only look at the bounds for the original region. So you don't look at the rotation. In this case, it doesn't make a difference, but it can sometimes. You don't look at the rotation, you just look at the original region you drew. Our formula is set up to integrate over that region, so from 0 to 1. Pi times the outer radius squared, that's 2 minus y squared squared, minus the integral from 0 to 1 of pi times the inner radius squared, that's 2 minus y squared, and now I'm going to go ahead and combine these into one integral again, and I'm also, at the same time, going to multiply out these squared terms. So 2 minus y squared squared is going to give me 4 minus 4y squared plus y to the fourth, minus, and 2 minus y squared will give me 4 minus 4y plus y squared. And now we'll simplify everything a bit inside the integral before we actually compute it. So we get 4 minus 4 here. Those cancel. And nothing else is going to cancel, but we can combine negative 4y squared with minus another y squared. So we'll make that a negative 5y squared plus y to the fourth plus 4y. Because we've got a negative of a negative there. And now we just continue with our integral computation. We get pi times negative 5y cubed over 3 plus y to the fifth over 5 plus 4y squared over 2, evaluated from 0 to 1. It's pi times negative 5/3 plus 1/5 plus 2 minus 0. Okay, so now we gotta find a common denominator here. We'll go with 15. So multiplied by 5 over 5, that's negative 25/15 plus 3/15 plus 30/15. That's going to be 8/15 of pi. So 8 pi over 15. Now, mind you, these are all volume. I haven't really been writing this, but it's some unit cubed. We're not really specifying units here. It's not a real-world problem per se, not an application problem. But you should be keeping that in the back of your head. You're dealing with volume. These are units cubed. So once you start talking about applications, you've got specific measurements, centimeters or inches or whatever. You need to think about those cubic units. All right. So now we'll do something a little bit different. Find the volume of a pyramid whose base is a square with side L and whose height is h. So this is different because if you're talking about a square pyramid, you can't represent this as a rotation of a curve. So remember, the whole purpose of the rotation of the curve thing is all about finding the area function. So the reason we were doing the disk method here is because the area of the cross section is pi r squared for a disk. But if we don't have the area, if we don't have a rotation about an axis or about a line, we're not going to get a disk area formula. So we have to come up with a different approach here. And most of these problems, the approach will be pretty unique per problem. So you just have to kind of work through the thought process to come up with something. But for this example, we'll specifically deal with a pyramid with a square base, so side length L, and whose height is h. So now I want to figure out some way to place this on a coordinate system so that I can come up with some sort of function to describe the area of each cross section. And there are a whole lot of ways to do this. So by no means should you think that the particular version of this I'm going to do is the only option. You can definitely figure out other ways to set this up if you prefer. But I find this to be the easiest one personally. So what I'm going to do is plot my pyramid sideways. So I'll put the point of the pyramid here at 0, 0. And I'll put the base of the pyramid here. And since the height of the pyramid is h, that puts us at x equals h here. And so the idea is that our base is down here, the point is here, So that's our pyramid. And what I want to figure out is, how do I get a area formula for these cross sections? And one of the things that we learned from geometry is that if the base of a pyramid is a square, all of its cross sections are also going to be squares. And so that helps us. So what I notice is that this point on this corner of this square is on a line. And this line can be given by the equation mx plus b. So slope times x plus b. But b is 0. The y-intercept is 0, which is why I pushed the corner of the pyramid here so that I would have a simpler linear function. The question is, what's the slope? Well, if the whole length of the side is L, then this thing is half of L. And the length is h, so rise over run. That's L over 2 over h times x. But we don't normally write it that way. We would simplify this to L over 2hx. So that's the slope times x, right? And now what I need is an area function based around that. Well, here's the key. That is half of the height. So that's our half of the length of a square, right? Half the length of the square side. So then if I want the area of the cross section, I have to double that 2 times L over 2hx, and then square it because the area of a square is the side squared. And of course the 2 over 2 cancels, so this becomes L over hx squared, which is L squared over h squared times x squared. So that was the whole key here, really. I just needed to figure out the area formula for our cross sections, and the rest of this is pretty easy. So now I set up my integral. My integral is from 0 to h of my area function. And my area function is just L squared over h squared times x squared dx. So L squared over h squared is a constant. We find the antiderivative of x squared is x cubed over 3 and evaluate from 0 to h. This gives us L squared over h squared times h cubed over 3 minus 0. And finally, the h cubed over h squared will simplify to h, and I get L squared h over 3. But what I want you to notice is that this is really just the area of the base times the height divided by 3, which is our general formula for volumes of pyramids. Okay, well that's it for that one. Thank you for watching.